Okay, today we're going to just, I'm going to pick out some problems from the 2019 FRQs. So we'll work through page 21 and 24. And our suggested homework will be just the 2019 FRQs, page 21 and 26. I know on the board I have 2018 and 2019, but if we have any leftovers FRQs, we can work on them a little bit next week as well. All right, so go ahead and read the problem. This is a calculator question. This is a rate in, rate out problem. Yeah, and then if you need solution keys or packet files, you're welcome to pick one up. Okay, so fish enter a lake at a rate modeled by the function E of t. Fish leave the lake at a different rate modeled by L of t. Both E of t and L of t are measured as fish per hour. They're both going to be rates. So part A, how many fish enter the lake over the 5-hour period? So all we need here is to work with E of t to figure out part A. So we want to be able to get something that is at the fish per hour level up to the number of fish. So you can set that one up for part A. And so part A is just identifying the need to take the antiderivative, get the integral for E of t. EBC, right? So, yeah, that's their
issue. For like when we're like taking the AP exam for like part A, part B, part C, and part D, are they weighted the same or is that or it's just
Yeah, these are just, I think when I made this is just predicted points, but they're not necessarily weighted the same. You're not going to know what the weight of each of the parts are, but they're going to add up to 9 points, one way or another. So a lot of times, each part is going to be somewhere between 1 and 3 points. But yeah, you don't know how their rubric is set up. All you know is you're trying your best to earn as many points as you can. But yeah, some of the details is hidden from you in terms of how they're going to award points. Okay, part B, what is the average number of fish that leave the lake per hour? So we still want something at the level of fish per hour, but we want the average number of that. So there's that hint, average value theorem for part B. So we want to take 1/5 of the integral from 0 to 5 of L of t. And our units will still remain as 6.059 fish per hour.
Are you using integral if it's asking for rate of fish per hour rather than just amount of fish?
Right, so we know the integral is going to give us a number of fish, right? But then we're dividing by time, divided by 5. So we're back to where we came from, even though there's integral involved. Part C. At what time is the greatest number of fish in the lake? So part C is quite a lot because we have to first find a formula that will tell us how many fish there are at any moment in time. And then we have to find a critical point. And then we have to test those critical points and endpoints. So this is whole extreme value theorem process here. But first things first, let's build out our formula that will tell us the number of fish at any moment in time. So this is a rate in, rate out problem. This is a formula that we can expect to see in these types of problems. So the idea is that the total amount that I'm looking for is equal to the initial amount or the given amount plus however much has been added in that time period minus how much has been removed in that time period. So we have a formula for rate at which fish is entering in. We have a formula for the rate at which fish is leaving, and we also have the initial number of fish in the lake. So this is how I'm going to set up my f of t equation. That's going to give me the number of fish in the lake at any moment in time after we consider all these moving parts. So now that we have our formula, we know we're looking for the greatest number of fish at any moment in time. So we know we have to set f prime equal to 0 to find our critical points. So f prime would be, this will be a constant that will drop out. The derivative of these two is going to make both these terms go back down to in terms of the functions here. So if I take the derivative of those, I'm going to be left with f prime, which is simply E of t minus L of t, right? I've applied the derivative for each of these terms here. That goes to 0. This comes down to E of t, and this comes down to L of t. Basically, second theorem. Getting that function down to a derivative level. So once we're here, we know our critical point is where f prime is equal to 0. So we set f prime equal to 0, and we are going to need our calculator's help to help us find that critical point, that x-intercept. We're looking for something that is between 0 and 8. And so we're going to have to graph that E of t minus L of t in our calculator. I'm looking at my coefficients. They're in the 20 and 4 range. So I think if I just went from negative 20 to 20, that should allow me to see a graph. I can just graph that curve, look for the x-intercept, and find that x-intercept. And now I have a critical point. So I'm going to be testing 6.2, 0, and 8 against my f of t equation. And then I have all the potential values where the maximum number of fish can occur. So I'm testing f of 0, I'm testing 6.2, and I'm also testing t equals 8. And each of them will go back into my FT equation. And I'm just churning them out, math 9, making the calculator find those values for me. So I'm just at the end, I'm just comparing these three numbers. F of 0 equals 0. F of 6.2 is 135. F of 8 is 80.9. And between those three, the greatest number of fish is at 6.2, 135 fish. Part D is my rate of change increasing or decreasing. So it's asking my F prime is at the rate level. It's asking is F prime increasing or decreasing at a T value. So basically it's asking for something at the F double prime level. So we know F double prime is just E prime minus L prime. And we can plug 5 in and we just look at the sign. If we get a negative second derivative, we know the rate is decreasing. If we get a positive second derivative, we know our rate is increasing. And that's just the math 8 process for part D. Page 24. Okay, I'll give you guys a minute before I talk about 24. So 24, this is number 4. I want to practice us to practice a little bit with related rates. Chances are you're probably not going to see an FRQ that's devoted to related rates, but you're guaranteed that some related rates is going to come up in on your FRQ. So be expecting that, and be able to recognize when something is going to require you to follow these related rate steps. If you're asked to find that if it's a word problem with time involved and they're giving you all this data that is good for related rates, then we want to be able to build out our derivative appropriately using our related rates concept, related rate steps. So let's look at number 4 here. Okay, we have a cylindrical barrel with a diameter of 2 feet, contains collected rainwater as shown. The water drains out through a valve at the bottom of the barrel. The rate of change of the height is modeled by dH/dt. So we have a rate at which the height is changing, or the level of the water is changing in the barrel. Find the rate of change of the volume of water with respect to time. So that's a big hint there. With respect to time, we know that there's that independent variable time that's going to flow through our equation. So we're going to have to rely on our related rates to find our derivative. But we know that with a cylinder, we understand that our radius is never changing, right? We know that the radius is going to stay constant at 1 feet. The height is changing over time, but the radius is not changing Doesn't matter how high, how much water is getting added or removed, that radius will never change. And because of that, we can just find a way to do a simple replacement in for our radius. It's not like cones. With cones, we have to keep track of the radius separately with the height. We have to go through similar triangles. We can't get rid of the variables. But with cylinders, we can just go ahead and get rid of the variable if we know that the value is never going to change as time passes. So we just go ahead and replace our radius with 1. And that way we have a much easier equation for us to find the derivative. And now we can go through our steps for related rates. So v becomes dv dt, the pi stays, h becomes 1 dh dt. And now we're ready to do substitutions into this equation to solve for the variable that we're looking for. So we're provided dh dt, we plug that in. We know the height at that moment in time is 4 feet. So we can plug in. Oh, just want to point out, we gotta be careful that we don't plug in values too early in our process. Some students may be tempted to want to plug 4 in for the h. If you do that, you lose that variable h. If you lose that variable h, you're not going to get that dh dt to show up. So just be aware. A lot of times these values that they give you are good for after the derivative to plug in, but it's not quite ready yet if you're trying to plug in before the derivative shows up. So we find the derivative. Now we can plug everything that we need to use, and then we can solve for dv dt. It goes negative pi over 5 cubic feet per second. And part B. When the height of the water is 3 feet, the rate of change of the height is, with respect to time, is it increasing or decreasing? So we're asking about, is the rate increasing or decreasing? That's the indication that we're trying to get us to move into that second derivative. So we're going to find d2h over dt2. We're going to find the second derivative of dh dt. So this becomes second derivative. H, we got to go through related rates. So we go through power rule first for h, and then we attach that dh dt. Once we find the derivative, now we can plug in anything that is available to us. Replace dh dt back in terms of h, and then you can replace the h with 3, but looks like all the h's cancels out. So all we're left with is a positive 1 over 200. We get positive second derivative, so we know that the rates must be increasing. Since my second derivative is positive. Part C, at time t equals 0, the height of the water is 5 feet. Use separation variables to find expression for h in terms of t. So this is where we can go through. So yeah, this problem is a shared AB problem. So these are all AB concepts here. So we're going to just separate our variables. H is on the left, T is on the right. I didn't cross multiply, but it's And cross multiply, move terms in a way where your h's are on the left and everything else is on the right. And anything that doesn't have to be on the left side, I prefer to just have it over on the right side. Because eventually everything has to come over anyways, so keep that left side as bare and as minimal as possible, only what is needed. We want to keep on that left side. And once we've done our full separation of variables, the left side is just power rule, the right side is also power rule. We take our antiderivative plus c shows up. And then I just decided to solve for c first for this problem, so I solved for c first, and then I work towards solving for h. But again, it's really an arbitrary decision, which order you want to solve h and c. So I solved for c first, and then I went through and took the steps to get h by itself. Now, once you get h by itself, don't worry about what that right side looks. Whatever mess it is, just leave it alone. Don't feel like it needs to have a certain form to it. As long as you have your your dependent variable by itself and your c is figured out, don't worry about what that right side looks like. Okay, so I encourage you guys to work through the rest of 2019 FRQs. And tomorrow I'll just pick out problems probably from 2018. So, bye, computer phones. This is. Okay.